Hello, 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 and welcome once again. Welcome everybody to Physics Rich, your one-stop channel for the preparation of IIT-JEE, Mains, Advanced NEET, and AP. Here we are doing the Awesomeologist series, and we are learning how to apply Bernoulli's theorem in numerical applications. If you've already watched the first two lectures, then this lecture is going to be super easy for you. You are going to be able to adapt to it very well. But if you haven't watched the first two lectures, I highly recommend that you go and you watch the first two lectures so that you can ease into this lecture very nicely. So guys, without further ado, let's begin learning how to apply Bernoulli's theorem in some more really awesome problems. So in the previous lectures, we have discussed the basics of Bernoulli's application. We did this one really nice problem in which I told you that when liquids curve, the outer region experiences a greater pressure, and when there is a greater pressure, there is a lesser velocity. When there is a lesser velocity, the streamlines are more spaced apart. In regions of higher velocity, the streamlines are more crowded. Then we learned this problem in which we learned how to apply the equation of continuity along with the Bernoulli's equation, and we learned how to calculate the flow rate. We also learned this problem in which we saw that Bernoulli's equation can only be applied along a single streamline. And then we went on to do another application of Bernoulli's equation where we came to a very important conclusion that even though the results of Bernoulli's equation look very similar to the third equation of motion, you cannot simply say that the third equation of motion is how the fluids are behaving. Okay, the results may appear to be similar, but they are not identical. And that's why we are going to learn this one very nice problem today. So let's learn what this problem is asking us to do. So we have, first of all, this is a very standard problem. Okay, this problem you can find in every coaching's module. You will find this in all good books. So it becomes imperative for us to learn how to do this. So this is a cylinder, okay? And I could have taken a hemispherical bowl or any other shape, but right now, for the sake of simplicity, I have taken a cylinder. And this cylinder is full of liquid, and the liquid is being poured out from this very tiny hole of area small a. This liquid is filled up to a height of small h, and the area of cross section of this cylinder is capital A. And now you're required to find out how much time it will take for this cylinder to be completely empty. Okay, so that's the idea. So how do we approach this? We approach this using the concept of streamlines. Now, at any given time, let's say t, and that's not equal to the initial t equals to 0. T equals to 0 would mean that the liquid is just beginning to fall out. Okay, but that's not what we're talking about. We're talking about some general time t. Okay, now at a general time t, the height of the liquid is x, and we have drawn a streamline from the top to the bottom. So this top region is exposed to the atmosphere, all right, and this liquid which is flowing out is also exposed to the atmosphere. So we can say for both points A and points B, the external static pressure is going to be P naught. All right. Now you see, guys, that if you've learned Torricelli's theorem, Torricelli basically says that if I allow liquid to fall out of a container which is exposed to the atmosphere in this way, then if the height is h or x, let's say just x, okay, then the liquid that comes out will have a velocity of square root of 2gx. This is Torricelli's law. Okay, we have learned this in our theory lectures. And we are going to apply the same logic over here itself. Okay, so applying Torricelli's law, actually Torricelli's law is nothing but an application of Bernoulli's theorem. And if you do not know how it works, then let me just quickly show you how it works. We can apply Bernoulli's theorem between point A and point B, and you can write that pressure at point A plus half rho VA squared plus rho Gx. This is Bernoulli's expression for the point A. Okay. Now this should be equal to pressure at point B plus half rho VB squared plus rho g height of point B, which is nothing but 0. Okay, so this is anyway gone. All right. So what is PA and PB? Guys, PA is the pressure from the top and PB is the pressure over here. All right. PA is the pressure due to the atmosphere from the top and PB is pressure over here. So PA and PB also just cancel. Okay. So now we are left with just this term. Let's remove this term. Let's remove this term. And also let's remove this term. All right. Now here is the thing that these are equal. All right, these are equal. One very important thing, guys, if you apply Bernoulli's, most of the time you will also see that you're going to have to apply equation of continuity as well. So can you say that the area capital A, which is this large area, times velocity at A is the flow rate? This should be equal to small a VB. All right. Now, capital A upon small a is a very large number, as you can see over here, because capital A is much bigger than small a. And according to this should be VB upon VA. All right. Now, this is a very large number compared to 1. So, can you say that VA is very small compared to VB? Yes, we can definitely say that, which means that even this term is now gone. Even this is 0. All right. So, if we compare these two terms only, all right, if we just simply say that rho gx is equals to half rho VB squared, then you see the rho gets cancelled and VB squared simply becomes 2gx, or you can say that VB is square root of 2gx. So this is what Torricelli said. This is what Torricelli's law is, that if the liquid has a height of x and it is open to atmosphere above and below, then the velocity with which the fluid will flow out is square root of 2gx. Now here's the thing, guys. So the important part is written over here. Let me just remove, no, actually I don't need to remove anything. You can just understand it from here itself, that if the liquid falls down in dt amount of time, how much time? Dt is very small amount of time. It falls down by a height of dx. Okay, so this length is, let's say, dx. This is dx. Then the volume that goes out is going to be ADX. What is A? A is the area of cross section. DX is the height. So tiny volume goes out. All right. And because this change in length is going to be negative, so we put a minus sign over here. This is going to be a minus ADX. And what is flow rate? Volume flow rate. Volume flow rate is nothing but the volume flown per unit time. So it's minus ADX by dt. Okay. Now you see, guys, that this flow rate, okay, which we have calculated, this flow rate has to be equal to, related to this velocity. And how do we relate it? We relate it like this. This is the flow rate minus ADX by dt. And this is also the flow rate, velocity times the area. And that's the mathematical blueprint of how we will solve this problem. After this, it's nothing but calculus. If you are good at calculus, then you can just simply integrate this and get the answer. How do you integrate this? Well, just simply take the like terms on one side, like this is dx and there's a root x over here. So I've taken the dx upon root x over here. And everything else remains a constant. You can do a little bit of cross multiplication. You can see that small a root 2g upon capital A will sit on this side. And then there's the dt, which will also go that side. And then you can do the integration. And in order to do the integration, we will apply the simple rule of algebraic integrations. 1 upon root x becomes x raised to power minus 2, whose integration will be x raised to power minus 2 plus 1 upon minus 2 plus 1. Okay. And then the integration of dt, which is nothing but t itself. Then you apply the limits. What are the limits? The limits will be that when time just begins, when there is t equals to 0, then the entire height will be h. And then after t amount of time, when the whole thing has been flown out, then the height will be 0. And then when you put the values of the limits accordingly, you get the entire value of time. Okay, as you can see, capital A upon small a, root 2 h by g. That is our answer. A very nice looking answer. Okay. So let's move on to another very nice problem that I would like to discuss with you. So in this question, we have a very large vessel. Okay, so this is like a very large vessel, and it's full of liquid. Okay, it's like full of liquid, and this large vessel has a hole. Okay, this is a hole, and this hole has a radius of r1. Now this hole is like kind of like covered with a concrete cylinder. What you see over here is a rectangle, but if you see from the top, it will appear to be like a cylinder. Okay, actually you should see it uh, from the top. It will actually appear like a circle. Okay, and then there will be another circle inside of this. Let's draw another circle. There will be another circle inside of this, and you can say that this circle will have a radius of the radius of the hole, okay, which is r1. This is r1, and then there will be the radius of the cylinder, the larger portion. Like you can assume that there's a cylinder which is coming from on top of it, and this is the hole, and liquid water is like coming on from all sides. So this will be r2. Now you see that liquid will be flowing in like this. Okay, liquid will be flowing in like this. The interesting part over here is that, guys, this thickness, okay, this thickness, let's take this thickness to be, what should we take it? Let's take T as the thickness, okay. So the interesting part over here is that, guys, that this is the top view, okay, this is the top view. But if you were to make the side view, you know what the side view will look like? It will look like this. It will look like this. And then there will be a hole over here. Okay. And then water would be gushing in from the sides like this. Like this. And then it will be pouring out from here. Okay. So I hope you can understand, like this is the side view. Like I've tried somehow making the 3D view, and this is the top view. Water is gushing in from all sides. But as the water is gushing in, it is getting lesser and lesser. Like you see, as it gushes in, it gets squeezed in. So it has lesser area of cross section to pass through every time it reaches close to the hole. Okay. So what happens? The area sort of reduces, and when the area reduces, the speed should increase because of the equation of continuity. So as we see that water gushes in from here, and as it reaches the hole, it becomes faster. Okay, this kind of like, you must have noticed this, like even in our kitchen sinks, in the kitchen sink, as the water goes closer to the hole of the sink, it goes faster, right? Because every time it moves closer to the hole, it has lesser and lesser space to be occupying. So it becomes faster as it goes to the hole. So here itself, we can see that it is going to become faster, and what we can say is that whatever velocity will be here, okay, velocity at this point, which will be, let's say, v1, okay, that velocity and the velocity which will be over here, some other point, let's say this is v2, these velocities will not be the same. In fact, v1 will be greater than v2. This is one definite thing that we can say. All right. Now let's get back to our original problem. So where is the point 1? So guys, this is the point 1. This is the point 1. Okay, and somewhere here, this is the point 2. Somewhere here, this is the point 2. Okay. Now what I would require you guys to do is to understand that I can apply Bernoulli's right from here to here. Okay. I can apply Bernoulli's along this streamline between the point 1 and 2. So how am I going to apply Bernoulli's? See, P1 plus half rho V1 square equals P2 plus half rho V2 square. This is how I will apply Bernoulli's, right? This is how I have been applying Bernoulli's throughout. Now, very interestingly, this is the whole, so P1 is nothing but the atmospheric pressure P0. And very importantly, which we learned in the previous question, this part is open to the atmosphere, okay? This part is open to the atmosphere, and this entire streamline, in this entire streamline, you can apply Bernoulli's. So definitely, from the previous question, we learned that this V1 has to be equal to root 2 GH, okay, because this height is h. So V1 square simply becomes 2GH. Now, if I put this over here, it just becomes rho GH. Now, this should be equal to P2, pressure at the point 2, plus half rho V2 square. Now, what am I looking for in my problem? P2 is the desired variable for me. This is what I'm actually looking for. So, I'm just going to rearrange this. I'm going to write P2 equals to P0 plus rho GH minus half rho V2 squared. Now, if I find V2, my life is set. Problem solved. So, let's hunt for V2, guys. So, we already know V1, and we know that V1 is flowing through this tiny, like very thin cylinder. What will be the area through which this V1 will be flowing? This area for V1 will be 2 pi R1 times T. Okay, 2 pi R1 times T. Can you see that the thickness is T? Over here also the thickness will be T. If I draw an imaginary cylinder over here, which you can see over here, so this sort of like this cylinder, okay, this cylinder, this is the whole one. So this will have a curved surface area of 2 pi R1 times T, where this is the R1 radius, okay. Multiply this with the velocity V1, which is root 2 GH. Okay, I'm applying the equation of continuity. A1 V1 equals to, now the area over here will be 2 pi small r, okay, 2 pi small r, and r, small r I'm assuming for this, for this pink cylinder, okay, this is small r, 2 pi small r T V2. All right, so this will have the velocity of V2. So I can see that certain things are getting cancelled very nicely. 2 pi, T, all of this is getting cancelled very nicely. And what am I left with? I am left with V2 as R1 root 2 GH upon small r. R1 root 2 GH upon small r. This is what I'm left with. And isn't that exactly what I was looking for? Yes, this is exactly what I was looking for. So let's put this over here. Oh, I think we'll need some more space. So what did we have? We had pressure, which is what we were looking for, was P0 plus rho GH plus rho GH. And then we had this V2 term to be put over here, half rho V2 square. So minus half rho, and what is V2 square? V2 square is going to be the square of this whole thing, R1 upon R whole square times 2GH. So I see that this 2 gets cancelled, this 2 gets cancelled. There is a rho GH over here and a rho GH over here, so I can take the rho GH common. And then I am left with 1 minus R1 by R whole squared. And that's my answer. So this is exactly what I was looking for. I was looking for the pressure at any of these, as a function of small r, which is any of this distance from the axis of this hole. All right. So this is the final answer. A very nice looking, beautiful answer. So guys, that's all for today. I hope you enjoyed today's lecture. And this is going to be all for the application of Bernoulli's theorem. And I will be back with more problems in fluid mechanics, which will involve more ideas and Bernoulli's equation too. So until then, stay physics rich.